All right, good afternoon, everyone. Welcome to the third Gen Chem Study Session of this semester. We want to give a special thank you to Dr. Taylor for joining us on this dreary Sunday. Hopefully the weather holds out and we don't run into any internet or connectivity issues, but we will do our best to get through this. Just so everyone is aware, this event is being recorded and it will be posted at a later date. Same with any questions and materials that we don't get through. With that being said, welcome, Dr. Taylor. The floor is yours.
Thank you. So just to remind everybody, so our next exam is exam 3, Saturday. Gosh, it's been a day. I got this. I'm going to keep drinking my caffeine. Saturday. Our exams are always on Saturday. Today is Sunday. That's today's date. Our exam is on Saturday, April 8th, 10 a.m. And a reminder that 10 a.m. is our starting date. That's when we pass out the Scantrons. That's when everything gets rolling. So you guys should be there before 10 a.m. 9:30, 9:45 is a great time to aim for. So I do have my periodic table up here in case we need it. Some general reminders of what we are covering or what we have covered for this exam. So chapter 17, we're basically in the latter half of 17. This is all stuff that we covered before spring break. So there was 1 week before spring break and we covered stuff about acids and bases. Now the weird thing here is 17.6 and 17.7. That is where Ka and Kb are. And we did ask y'all some questions about Ka and Kb back on exam 2. But keep in mind, we're still going to need Ka and Kb for this exam coming up. So I'm going to go ahead and still say 17.6 and 17.7 are valid for this upcoming exam, because we're going to do questions about K that involve you knowing and remembering what Ka and Kb are. 17.8's conjugate acid-base pairs, also a concept that keeps returning. 17.9, that's on polyprotic acids. So that involved things talking about how to deal with the fact that protons come off one at a time when you have more than one of them. And so these things tend to have things like 2 different Ka values. So that's what was going on in that one. And there was some ways to specifically work with those. 17.10 is salts. 17.11, you might notice there's a big red X through it. That's oxides. We didn't cover oxides. We're not covering oxides this semester. They are kind of cool, but they wind up being mostly a memorization tool. So we got rid of those. Lewis acids and bases are on the exam. So that's 17 stuff. Then 18 is what we've been covering since we've been back from spring break. For the most part, I know this list looks really short for those of you who might remember. These things tend to be a bit long. Buffers, titrations, KSP. So yes, I made that chapter look like it's really short when in fact it is not, but we can definitely have conversations about any of those, better refresh on what those are. And chapter 15, we're not going to get through all of it. Most what we are going to do is entropy. Its definition, comparisons, and some calculations. The one thing I will say with chapter 15 is we are just doing entropy. There is another thing, and with entropy is either S or delta S is entropy. There is another thing that some folks may be familiar with if they've had chemistry before, which is going to be an exam 4 topic. So exam 4 topic is going to be this other thing called delta G or Gibbs free energy. So for folks that are waiting for that, that's going to be an exam 4 topic. So we are going to do this teeny tiny amount of chapter 15, which is mostly introducing entropy and doing a teeny tiny bit with entropy. So that's I know I didn't grab page numbers, and for the most part, I didn't grab section numbers. Honestly, that's because I wanted to double check with my colleagues to see if we're stopping at 15.3 or 15.4. So as I needed to double check with them before I officially said anything. That's why this list is kind of vague. But that at least will give you all a general idea of what is covered and what we are doing. So what I'm actually going to start off with while I'm waiting for questions to come up in the chat, I'm actually going to talk just a little bit about entropy even though it's like the very last thing. So first of all, entropy. This is not enthalpy, by the way. And you have my sincere apologies that those two words sound so very similar. So we did enthalpy, which is delta H, which has to do with things like exothermic and endothermic. That will be a returning concept in chapter 15, but entropy is something different. Usually when people hear about entropy, they usually hear about things like disorder, sometimes chaos. Personally, my favorite definition of entropy is actually microstates. And really what all these have in common is this is the idea that if you are talking about what happens in the universe, what happens naturally, things tend to go towards more disorder. Things tend to go towards more microstates. So for example, the air in the room that I'm sitting in, the air in the room that you're sitting in tends to be randomly scattered. All of the different air particles are randomly distributed. Nobody ever worries that all of the oxygen in the room will suddenly congregate to like one corner of the room and we will all suffocate because suddenly all of the oxygen is in one location. Nobody ever worries about that because that's not what happens in real life. In real life, that oxygen disperses all throughout the room. It goes for as many potential locations as possible. So this notion of microstates or options, the more options something has, the more entropy it has. So that oxygen is going to be randomly distributed. And that gives you somewhat of an idea of entropy. So some other examples of entropy, we often do comparisons. So you can think about things like the differences between a gas versus a liquid, and the fact that in a gas, you have those particles that can just sort of zoom around, and they're going to bounce off of walls and they'll slide past each other, and they can be just about anywhere in the room. This is, all those little lines are supposed to be movement, by the way. That's what all of those are. Whereas if this is a liquid, they can still slide past each other, but they're all going to be connected. They're all going to be hanging out together. They're all going to be having intermolecular forces together. But at least they can move. They can kind of swish back and forth, but they're going to be a bit different. So we would say that the gas has greater entropy because those particles have more options of where they could potentially be. They could be up at the top, they could be down at the bottom, they could be in the middle, they could be anywhere. The liquid, gravity is going to work much better on the liquid. The liquid still can move. Those particles still have movement though. So it will still have some entropy, but not as much as the gas. And what you might then imagine is if we then compare it to a solid, the solid, those are going to be essentially locked in place. And while they can still certainly vibrate back and forth, they're not going to have nearly as much movement even as the liquid. So that solid is going to have the least entropy out of the group. So there are a couple of different ways to talk about entropy and some different situations besides just solid, liquid, and gas that will hold you responsible for the exam. But that at least gives you a little bit of a taste of entropy and definitions. I'm actually going to go ahead and do one entropy calculation. And then after my calculation, I'll ask for questions. Mostly because I know sometimes I don't get to do the problem I planned for. So this one's asking, what's the change in entropy for the reaction? And it gives you a reaction, and then it gives you a table. And this table should have had things a little bit more filled out. Did I grab a screenshot? Whoops, that's where I grabbed some of my information from. I actually wanted to just grab the headers from them so you can see what those look like. So this is in entropy with a little circle symbol for standard, and it's in joules per Kelvin times moles. So entropy's got a little bit of a different unit than what we may have seen before. Again, for this exam, the nice thing is that it's just going to be entropy, and we're not going to be dealing with this delta G yet, and we're actually not even going to bring back enthalpy quite yet either. From this screenshot, what you might actually notice is that all of my values for entropy with the S are actually all positive values. So since entropy is talking about microstates, unless we're under really special circumstances, entropy usually has a positive value. Sometimes can be 0, but that's it. So it's either positive or 0. I can't think of a time where you should have a negative entropy in this sort of a situation, especially since we're under standard conditions. So it should be at 25 degrees Celsius. Okay, joules per Kelvin times moles. Standard joules per Kelvin times moles, just to have my units on there. Mostly that we're in joules. You're okay, buddy. Down, bud. My dog is telling me that there's thunder outside, by the way. It's okay. My partner is home. My dog can go protect my partner. Everything will be fine. All we're going to do for this particular calculation is something that might seem familiar to you. It's okay if it's not. But what we are going to do is we're basically going to take all of our products, multiply them times their coefficients, and subtract all of our reactants. We are looking for the change in entropy. And since we're looking for the change in entropy, we're going to use the change is equal to final minus initial. So we are going to use products minus reactants. Again, if this sounds familiar to you, it would be familiar back from Gen Chem 1. So that's why there was that giant if in front of it. But if not, we're just going to talk about it and work through it right now. So I'm going to take all of my products. So in this equation, I have I have carbon dioxide and water. So I'm going to just take my value for my carbon dioxide, which is 213.6, plus 2 times whatever my water is because of the coefficient. So 2 times 69.9. And then I'm going to subtract all of my reactants. So that's all of these guys. So my methane is down here, and my oxygen's over there. Let me get anything in order. 186.2 plus, but add up all my reactants together, 2 times whatever my oxygen value is, 205. So I should get 591 minus 326 for a grand total of positive 265. That is a entropy calculation. So as far as your exam goes with entropy calculations, this is the kind of thing that you'll be doing. Products minus reactants using stoichiometric coefficients along with values out of a table. So the biggest part of this typically is keeping track where that subtraction sign is. So that's why I do usually go ahead and do that in those 2 steps, so that I can keep track that all of my products have a positive value, all of my reactants then get subtracted to make sure that I've got my calculation correct. Also, it's a little bit easier than to do it by eye and say like, all right, I got a positive 200 something. I had 500 something minus 300 something. Positive 200 something is about right. So it also helps me to do a quick double check that my calculation is correct. So now that I've done a little bit of an introduction, where are we on questions so far?
All right, so far we have 4 questions. All right, first one is, could we work on some acid-base titration calculation, please? Such as strong acid and weak base, or weak base and strong acid. All right, next is, how do I choose the best indicator for a weak acid or strong base in titration or titration?
Okay.
Can we work on buffer solutions?
Okay.
Next is, can we talk about the conjugate acid-base pairs and how to describe the pH based on the strong present species in the solution, or strong present species in the solution, sorry. And the last
What
one.
was that? What was the pH based on what? I'm sorry.
Oh, pH based on the strong present species, or yes, yeah, strong present species in the solution.
Okay.
All right, and the last one for now is, can you go over each type of titration and the difference in method between each?
Okay. Anything else?
That's all for now.
Yep. Okay. So, let's go ahead and start with, we'll start with titrations. So for the record, yes, this is what I anticipated doing the most of. But what do I want to do? Let me grab a weak base because that's what we usually get as much practice on. Pyridine. Let's use pyridine. 1.7 times 10 to the negative 9. Great. Okay. So I wrote this down. I know it just looks like no one else does. C5H5N. Okay. So let's titrate pyridine, which is a weak base. So, okay. That's too small. A beaker contains 150 milliliters of a 0.12 molar solution of pyridine. I'm not going to get my subscripts on here because that takes me just a little bit too long. KB equals 1.7 times 10 to the negative 9. I will actually put my superscript in real quick because that one's going to bother me. Superscript, there we go. What is pH after 50 milliliters of a 0.15 molar solution of HCl is added? So, a couple of things. There are a lot of numbers in this problem. So one of the things that I've been mentioning to some folks, and I will mention it now, is titration problems are long. They have more steps in them than other problems. So for those of you that don't like titrations or are trying to get better at them, just do recognize the fact that while the tools that we're going to use to solve these are not particularly new, the combinations can be new, and none of these will be a one-step problem. So that means that these problems will be longer than ones we've done before. So what I am going to go ahead and do first is just keep track of what I have, because there's a lot of stuff here. So one, I'm told that I have a beaker, and the beaker has 150 milliliters of a 0.12 solution of something of pyridine. Cool, I guess. They gave me a KB value for it. So this is probably a base. I know we already know that it's a base because of where I pulled the information from, but bear with me. Of some stuff. And then to it is being added something else. This is 50 milliliters of a 0.15 molar solution of HCl. HCl, this one, you should be able to recognize. So that list of strong acids and strong bases, you do still need to have memorized because we should still be able to know that this is a strong acid because it's one of the ones that you have memorized. That list is back from exam 2 stuff, so you may have to go back and refresh. What are my strong acids? What are my strong bases? But you do want to have those memorized because that's going to help you through problems like this. So they're going to be added together. I have a strong species. Because I have a strong species, the very first thing I'm going to do is react everything together in moles. This is going to be your first step in every titration. So for the person that wants to know what to do in each type of titration, it doesn't matter what your titration is. The very first thing you're going to do is react things in moles. Because we need to know what we actually have left over, and then we can actually assess how to solve for whatever we're solving for. It is worth taking a moment to note that the problem asked what is the pH. So I do want pH at the end of the day. I am going to be looking for hydronium or hydroxide concentration so that I can do that. But right now, problems is to react in moles because I have this strong acid and I need to figure out if that's what I have at the end or not. So in order to react everything together, this is actually back like a limiting reactant problem, and I need moles, not molarity. So that's the very first thing that we're going to go ahead and do is get everything in moles. So I have this base of this pyridine, so I'm going to go ahead and take and multiply. So what I'm doing is I'm keeping in mind that molarity is equal to moles divided by volume in liters. So therefore, I can take my molarity times my volume in liters to be equal to moles. So all I'm going to do is multiply my molarity times my volume. It would have been nice if I had made sure I put molarity right there. So I am going to go ahead and change my milliliters to liters because that is easier for me personally. I know some folks really like millimoles. If that's you, go for it. You are certainly welcome to use millimoles. I know that does sometimes make the math a little bit prettier. So if that is you, go for it. You are more than welcome to do so. I just always use moles and deal with the little bits of scientific notation. So whatever you would like to do is your call. I am familiar with both. So if this is one of those back of the Scantron short answer problems, I can read moles, I can read millimoles, so can all the instructors. I should label these numbers as we go along. So I now have stuff in moles. So I have my strong acid moles, those are in red. I have my weak base moles, those are in blue. I'm going to react them together. So I know that my HCl is reacting with my base. I'll go ahead and write out the chemical formula. I got to admit, I don't really care what that is, aside from the fact that it's a base. Similarly, there's different ways to keep track of everything. So the thing I do care about is I'm going to have C5H5, and you can add the extra hydrogen wherever you'd like. I'm just going to put it there to kind of make a point that it is going to be connected to that nitrogen. And technically, I've got this chloride ion that's left over. The question is asking me about pH. That chloride ion will not affect pH, so I really don't care about it. Won't affect pH. And oftentimes you'll actually see that the chloride ion is left out of both sides of the reaction, and that all we're actually paying attention to is the strong acid. That's very normal, but that's up to you whether you keep it in or keep it out. Some people get a little bit frustrated when the chloride ion disappears. Some people get a little frustrated when you leave it in because it's extra stuff to write down that you're not going to use. So your work, you get to choose. So my hydrochloric acid, there is 0.0075 moles of that. My weak base, 0.018. I don't have any of this stuff. I don't care about the chloride, so I have to admit I'm not going to keep track of that. Whichever number is smaller, we're going to subtract. So I'm going to subtract by 7.5, and this is what I'm also going to add to the other side. Now, this is something, this addition here is something that we only do when it's a weak titration. So we really only worry about this addition with weak species, because when we have a weak species, we have conjugate species. And whenever we have a conjugate species, we do care about that conjugate species, because that conjugate species might be the only thing we have left over if it's the equivalence point, in which case that's going to dominate the titration because it's the only thing we have. Or it might tell us that we actually have a buffer system. And if we have a buffer system, solving for pH is going to get a little bit simpler than if we have to use an ice table. So whenever there's a weak species, we have to keep track of the conjugate because it will likely affect the pH. So we are going to keep track of that conjugate species for that reason. So hydrochloric acid, it's gone. My weak base, not gone. 0.015. Its conjugate acid suddenly is on the board and there's stuff there. So now that I have done my first step, react in moles. So this is the reaction in moles. Now I can take stock of what we have. So we have two things in solution. We have a weak base and we have its conjugate acid, and they are within 10 times of each other. What I mean by that is when I make them a ratio, I will get a number that is either between 1 and 10 or is between 0.1 and 1. So they are close enough to each other that this is a buffer. So since this is a buffer, I can use Henderson-Hasselbalch. pH equals pKa plus the log of AHA. Now, I know that there's another equation for Henderson-Hasselbalch. Frankly, this is the only one I ever use. I covered the other one when I taught it in lecture because some people really like it. If you are one of those people, again, that's wonderful. Just like my opinion on millimoles. If you really love millimoles, they certainly work. There's nothing wrong with them. If you really like the POH equation, it certainly works. There's nothing wrong with it. I am just going to work this one way. However, for simplicity's sake, because I'm still going to have to do some amount of work to get everything together. Actually, the first thing I'm going to do, since it's on this page, is go ahead and mess with this log portion and show you what I meant by that 10 times. So I have two numbers that I'm looking for. So I need to keep in mind that this top number is my base and this bottom number is my acid. They should be conjugates of each other. So my base is the 0.0105 number. My acid is the 0.0075 number. So all I'm doing is looking at the fact that I have a base and its conjugate acid, and looking at the log and my ratio. My acid portion goes on the bottom, my base portion goes on the top. So then I can go ahead and make that ratio. And when I do, that log of 0.0105 divided by 0.1275, this then is going to become the log of 1.4. So again, I needed that number to essentially be in between 0.1 to 10, because that means I would have a ratio where my conjugate acid and base are within about 10 times of each other, which is the range of a good buffer. So I got one number, I've got the log part. pH is what I'm solving for. So the pH is what the question asked for. So the question asked for the pH, which means the thing I have left to deal with is pKa. So I need the pKa, and I don't have it right now. So now I have to figure out how to get the pKa. Well, I've got something to help me. I have the Kb. That's not the pKa, so I'm gonna have to do some extra work. But we know how to do this. We know how to do this. There are two different ways to do this. Whichever one comes to your mind first is the way you should do it, because both of them work just fine. So you have two options. One, you might remember that Kw is equal to Ka times Kb. And the problem didn't say, but we are always going to be at 25 degrees Celsius. So we could go ahead and plug this in. And figure out that our Ka value is 5.88 times 10 to the negative 6, meaning my pKa value is 5.23. And that is what I wanted. I wanted my pKa value. So I'm going to go ahead and put it in the equation. And then I'm going to come back and I'm actually going to show you the other way we could have solved for pKa. Because this is that part where I don't want y'all to be like, oh no, she did it the way I would not have thought of, and try to relearn something, because you don't need to relearn it. Because there is another way to do this. So the other way to do this, still using that same Kb value, because that's the thing they gave us in the problem. The other way to do this is to say, you know what? I know how to, one thing, hold on. I realized I did that without showing off. pKa is the negative log of the Ka value. So that was the negative log of 5.88 times 10 to the negative 6. That's how we got a pKa value of 5.23. Sorry. So if we didn't do it this way, but we want to start with our Kb value still. So we still know that the Kb value is equal to 1.7 times 10 to the negative 9, and the goal is to get to that's the Kb value. The Kb value. And the goal is to get to pKa. The other thing we can do is we could actually solve for pKb, which is in fact the negative log of Kb. So I could take the negative log of 1.7 times 10 to the negative 9. And get 8.77 as my pKb. And then, remembering that 14 is equal to pKa plus pKb, I could go ahead and do a little bit of subtraction. 14 minus 8.77 to be equal to my pKa. And I get a pKa value that hopefully looks familiar, 5.23. So I get the same pKa value no matter which way I do that. Frankly, that's because we're using the same Kw relationship, just one way we took the negative log of everything, the other way we did it slightly differently. So it's actually the same math, just with logarithms in different ways. So no matter which way you did it, you get the same answer, which means we can go ahead and come down here finally and solve. Two, 3 plus that log. Okay. So what is the log of 1.4? Log of 1.4 is not a big thing. That is 0.146. I had more base than acid. Yes, I have more base than acid, so I would expect my pH value to be a little higher than where it started. So this is addition, just like it should be. Good. pH 5.38. Done. Sorry, this is my OneNote crapping out on me early. Oh, I change ink color. Sometimes that fixes it. Just quit out of OneNote and bring it back. There we go. Let's go ahead and write that out one more time. Now that OneNote's going to cooperate. 5.38. So one of the things to note where we were is we did go ahead and react everything in moles. We did that. Then after reacting everything in moles, we went ahead and figured out that we did in fact have a buffer situation. So since we had a buffer set up, we went ahead and utilized our Henderson-Hasselbalch equation since we had both conjugate acid and conjugate base present. So that's where we used this equation because we knew we had both of those there, and then got our pKa value so that we could continue on. How are we doing on questions out of the chat?
All right, as of now, we have a few more questions.
Mhm.
All right, the first one is, can you go over salts and how to know when they have an effect on the pH?
Okay.
Next is, can you go over identifying Lewis acids and bases when given an equation?
Okay.
And the last one for now is, could you go back to that first entropy question, please? They said they got a different value.
So my entropy question. So products, there's my carbon dioxide, my water. Oh, I know what I did. Yeah, no, we would get a different value because I switched something at the last minute. Oh, good catch. Good catch. So my products, I apologize for that. So let's go ahead and go back to the entropy question and redo my calculation, because one of the things that I had done is I had swapped my equation at the last minute. So I do apologize. I'd come prepared and then I decided to change something before I was done. 353.4. So anytime you're preparing for a group of people, should do more preparation apparently. So making sure that we actually add 213 plus 2 times 70. 70 times 2 is about 140 times 200, 340 plus 10, 350. Just do more mental math. Apparently that'll save me. Subtracting 186.2 plus 2 times 205 is 596.2. 353.4 minus 596.2 is negative 242.8. This is the only thing I miss about doing these live, is because when they're live, we catch that error way faster, way faster than when we do these recorded. So for those of you with the recording that are displeased, you have my apologies. This is the one thing that is worse when we're doing things recorded and I don't look at the chat. So that should be better. But I won't know for about 20 minutes. Okay, so a couple things in moving forward. One, so for the person that wanted each type of titration, I can do examples of, I will go ahead and still do examples of now a weak acid with a strong base and a strong titration. Technically, there are like 15 titrations if you are talking about before you've added any titrant, at the equivalence point, before the equivalence point, after the equivalence point. Okay, that's only 12. Because that's for, so I am not going to do 12 different titration examples. That's not going to happen. But I can go ahead and still talk through a couple of different setups. So one of the other things that we can go ahead and do is, let's go ahead and we just did a weak base, strong acid. So we'll go ahead and do a weak acid, strong base. So we will still go with, what is the pH? Bigger. What is the pH of a solution of 200 milliliters of, I need a weak acid. Good. Nope, not that one. Do I want phenol? Sorry, I shouldn't have made that noise. I'm gonna grab better stuff. I really only want one proton. I'm gonna grab better stuff. Oh, I know. I was looking for diprotic when I did this. I did this to myself on purpose. We'll go ahead and grab phenol. We're gonna go ahead and use phenol as my weak acid. But I'm actually going to use HA as my weak acid and use 1.3 times 10 to the negative 10. Weak acid of phenol, Ka equals 0.3 times 10 to the negative 10. Superscript. Oh, I need a molarity, 0.2 molar. Phenol, once it reaches the equivalence point with a 0.1 molar solution of, we'll use KOH. So this one's a little different. This one's a little bit different because I am going to try to do somewhat different titration problems, just try to show off a couple of things. So we are going to abbreviate phenol as HA to make my life easier. I have still some information about this. So I do have this notion that I've got 200 milliliters of a 0.22 molar solution of phenol, which we're just going to abbreviate as HA for a generic weak acid. And I have a Ka value for this. Lovely. This is not a very good acid. And I still want the pH, very similarly to what we did before. So I still do want the pH. Once it reaches the equivalence point with a 0.1 molar solution of KOH. So this is different because instead of trying to figure out what do we have in solution, how much of the stuff do we have, it actually tells me I am at the equivalence point. So I don't have to guess where I am in the titration. The problem says we're at the equivalence point, which begs the question, what is the equivalence point? So the equivalence point is going to be where our strong, whatever this is, our strong species has completely reacted the weak species. Or the titrant has completely reacted whatever was in the beaker. So to figure out completely reacted, we are actually going to do a very similar setup to what we did before, because one of the things I'm going to need is I actually still need to know some information. So to demonstrate this, what I need to know is I've got my weak species, my phenol, and we've added all of this KOH, and that is going to leave me with its conjugate species. So I'm going to have a conjugate base. And what I know about the equivalence point is at my equivalence point, I'm going to have used up all of my strong species. I'm going to have used up all of my weak species, and all I'm going to have left is the conjugate at the equivalence point. So that goes to the definition of equivalence point. So the thing is, since this conjugate base is the only thing I'm going to have, I need to figure out how much of it I do have. So I still need to know how many moles I have. So 0.2 times 0.22 gives me 0.044 moles of this, starting off with none. I know that I don't wind up with any of this, so I have to have the same amount. So even though we didn't actually necessarily have the information about the strong base, I have to have the same number of moles of that strong hydroxide as I have of my weak acid, so that this zeros down here are true. So even though that number wasn't given in the problem, because it said that we're at the equivalence point, I have to know that. So that's how I know, because of the equivalence point. So I've got a weak species. I don't have its conjugate, so this is not a buffer. And it's not a strong species, so I can't just plug in to a pH equation. So really, what I have now is I have a weak base question. So that's all I have left. I need to find the pH given a weak base. This is now an ice table problem. A good old chapter 17 ice table problem. But a good old-fashioned ice table problem would be in concentration units, and I don't have those right now. So I actually have to do some more math. So right now, I have moles. We need KB and ice table. So therefore, I actually need molarity. Good news, molarity's got two components, and I have one of them. So molarity, I've got my moles. And now what I need is I need liters. But I need liters. The thing though is that we actually added two things together. We added a weak acid together with a strong base. So which means the volume changed. our volume is not 200 milliliters because that was the volume of just the acid. We added a base to it. How much base did we add? Oh, we have to solve for that ourselves. But good news, we figured out how many moles we have. So now we still have to do the math. So we know that there's 0.1 molar of my KOH, and we know that we needed 0.44 moles of that KOH. Molarity is equal to moles divided by volume. So therefore, I can go ahead and rearrange this equation, or I can just plug things in. 0.1 is equal to 0.044 divided by volume. Can switch things around. My volume is equal to 0.044 divided by 0.1. My volume is equal to I don't trust my math anymore, 0.44 liters. So now I know how many liters that were added, because this is the volume of just my KOH. So what I actually need is that's my volume of my KOH. I now can add that to the volume of the original 200 milliliters. So this becomes 0.2 plus 0.44 liters. I should also tell you, I just made that prettier. I need to actually add those numbers. We as a teaching team are aware that these problems are long. So do be aware that we will ask you conceptual questions about titrations, because if we just asked you like 15 titration questions, most of y'all would not finish. I probably wouldn't finish. Let me rephrase. I probably wouldn't finish. Or I would be working really fast. So realize that there are different ways to ask. And really what I'm trying to do is I'm trying to ask questions in different ways so that we're using conceptual information as well as calculations. So that's part of what I'm doing in the examples that I'm choosing, is I'm choosing to try to use some terminology so that we can look at some various components as we go along. So I have a molarity for my conjugate base. That's what I have. Since I have a conjugate base in solution, this does in fact form hydroxide. Since it forms hydroxide, I am dealing with Kb. So you guys are welcome to go ahead and do, we don't care about water, minus x plus x plus x, 0.06875. I'm hanging on to all those digits just in case I need them, x and x. I really need a Kb here because this should be x squared divided by 0.06875 minus x. My Ka is right here. So I can go ahead and solve Ka times Kb. 1 times 10 to the negative 14 is equal to 1.3 times 10 to the negative 10 times Kb. Yes, okay, sorry. I was just taking a moment to look and double check. Kb 7.69 times 10 to the negative 5. I'm going to redo that math one more time, just to make sure. Yep, okay. So since we have the conjugate base, I therefore should have hydroxide. So therefore I should be dealing with Kb, 7.69 times 10 to the negative 5. I'm going to go ahead and do the X is small approximation. So there is actually a way to basically make this all go a little bit faster. It doesn't matter for me right today. 7.9. The reason I'm going to use the X is small approximation is because we're in a titration problem. And I wish I had set up these numbers to make sure that that works, but I'm 0.06875. So I'm looking for the square root of 5.288 times 10 to the negative 6. X is equal to 2.30 times 10 to the negative 3. That is hydroxide because it's a base. What did the question one again? I don't suppose the question one POH, did it? pH. So we just solved for hydroxide concentration. We know one hydroxide concentration, but we're going to use it. We're going to go ahead and solve for POH, and then get to pH. POH 2.638, pH, but it's a base, and we know that this is a base, so we do not want a pH less than 7 when we know that it's a base. 11.36. Phew! Gosh, that took a long time. Okay. That's 2 titration problems and an entropy problem in about an hour. But utilizing some various pieces of information. So just to remind you of a step that I skipped that I should have done, because this is the reason why it's better if I had written these out ahead of time, but there are only so many hours in the day. One of the things that we do before we get started when we're making the X small approximation is we're supposed to take 400 times the K value, whatever that is, versus the original concentration of acid or base, whatever that is. So here, 400 times 7.69 times to the negative 5 is 0.03076, which is smaller, but just barely, smaller than 0.06875. So we can use the X as small approximation. I cut it really close. I cut it real close. We won't do that to y'all in exams. It should be a little more different, but it was okay. It's less than 5% ionized. Everything's fine. And this problem, we're not doing the quadratic with a titration problem. No quadratic with titrations. No. Which is really the reason why I just kept going, because long enough as it is. Okay. So we dealt with equivalence point, having just a conjugate species, having to solve for a new volume. Did a lot of stuff. Where on earth is my list of questions? Okay, so I have not done most of these. I did the strong acid weak base. I'm checking that one off. I did some acid base titrations. We haven't looked at graphs at all. And conjugate acid base pairs, I think we kind of did those. Let's see. Let's left. Do one that does. Let's do Lewis acids and bases. We're gonna do Lewis acids and bases, and then we'll do. Well, then I'll take some more questions, which will probably result in more titration problems. But we did 2 titration problems, so take a little break and do Lewis acids and bases. Lewis acids and bases. Okay. First of all, Lewis acids and bases are just a broader category. So what I mean by that is we've been doing a lot of stuff with Bronsted acids and bases. That's all the titration problems. If you know that something is a Bronsted acid and base, it is also a Lewis acid or base. So what I mean by that is hydrochloric acid, HCl, that is an acid. It is still an acid in Lewis acids and bases. So things that you know that are bases because of how they act in titrations still are bases when you go to Lewis acids and bases. Things that you know that are acids are still acids. So that's the first thing that I'd like to start off with, just because if you have something that looks like this, that H plus should look like an acid. This ammonia, we've used it before as a weak base. It is still a base. And this actually winds up being true for both a Bronsted definition and a Lewis definition. So we can talk about these as proton donors and acceptors, but we can also talk about them as electron donors and acceptors. So it's different when we think about Lewis acids and bases, because now we have an electron pair that's being donated instead of just talking about the proton. But notice that if I had just slapped up that equation, most of y'all would have been like, ammonia, we've been using ammonia as a weak base since like the beginning of March. H plus, that's been an acid since the beginning of March, or before that, I don't remember anymore. So, but this is still true. So this counts as a Lewis acid, counts as a Lewis base, counts as a Bronsted acid, counts as Bronsted base. So if you can identify it via Bronsted, counts as Lewis. Second, but of course the grand, oh no, I restarted you computer. So, but the grand question, of course, is, but what if you can't? What if it doesn't look like that? So if it doesn't look like that, then it could look a lot of different ways. So one of the things, I'm trying to think of a new example that is not what I've done in class before, but I think we have to fall back on stuff I've done in class before. Let me actually grab Lewis acids and bases examples, like the very last slide here. Great. I'll just grab this one. It's my favorite. Actually is my favorite example for a lot of different reasons. So here's an equation. All the stuff that I had rambled on about Bronsted acids and bases don't apply here. But there are some things that can help. So when I am looking for Lewis acids, if that's what I'm looking for, I'm going to look for the following things in this order because it's going to make my life easier. One, I'm going to look for stuff with a positive charge. A Lewis acid is an electron acceptor. Electrons are negative. If I have something with a positive charge, it's more likely to be attracted to a negative thing. So positive stuff, more likely to be a Lewis acid. Positive charges, much easier to locate in equations. They just are, right? It's the way we write them out. Same thing when I think about like looking for a car in a parking lot. Probably going to tell you if it's a car or like an SUV because it's easier to see it if I know which one of those two I'm looking for. So first thing I'm going to look for, do I have something with a positive charge? Oh, I do. Look at that. Conversely, if I was looking for a Lewis base, which is an electron donor, first thing I'm going to look for is something with negative charge. Because, again, I'm looking for something with extra electrons. So I want electron pairs. And if I've got a negative charge, it's going to have them. It's going to have electron pairs because it's got negative charge. And oh, look at that. I got that. So I can label that thing as a Lewis base. I can label this thing as a Lewis acid, and I can go on my merry way and I'm done. And just based on charges alone. But what if that's not enough? So the other thing I'm going to look for, this too. So in Lewis acids, the other thing I'm going to look for is I'm going to look for third period and below. What I'm looking for is I'm looking for d orbitals. I'm looking for things that could accept additional electrons. So that's the periodic table. Scrolling, there we go. So when I say third period and below, I'm looking for, there's my threes. So I'm looking for elements that are in my third period or lower, because these guys all have d orbitals. So they are going to have that option of having more places where they could stuff electrons. Back in Gen Chem 1, we referred to this as an expanded octet when they could do that. Now we are in a phase where we're still thinking about where can I stuff extra electrons, but now we're thinking about is accepting electrons. These things make better Lewis acids. And I'm pretty sure that that thing that we had for Lewis acid is, I think in this case, this doesn't work as well for the example we were just using, because I think we had cadmium and iodine, and they're both down there. So in this case, the example that we're working with, they actually both have those, which is why we don't start there. But things that are third period and below do the orbitals, more possible for them to accept electrons. So a lot of times you actually see, your transition metals as Lewis acids, because a lot of times those transition metals are the reasons why we needed to expand the definition of Lewis acids and bases to take in those things. Third period and below. Other thing, double bonds. This one's not as obvious, and it's the reason why for Lewis acids, I think about this one last. But what double bonds typically allow molecules to do is they allow them to move some electrons around. So my carbon here could basically force that oxygen to take on more of those electrons, and then my carbon now has basically a temporary positive charge. So double bonds can also allow for Lewis acids to take place. But again, that's going to be usually the last thing that you look for when you're looking for Lewis acids, because then you actually have to deal with Lewis structures, which takes more time. So if you can identify it by charges, do it with charges. Then you're looking for third period and below, some d orbitals, double bonds. Lewis bases, we already talked about things that are negative. We are also going to be looking for electron pairs. So this is often things like so again, we're back in dealing with Lewis structures themselves, thinking about ammonia and the electron pairs that are there. We can also think about a hydroxide, which granted, hydroxide does have that negative charge going for it, but also thinking about the electron pairs, the iodine, the iodide ion, electron pairs. So more electron pairs, more likely to be a Lewis base. So hopefully that helps with Lewis acids, Lewis bases. One recommendation I would also recommend with this is to go ahead and check out those end of chapter questions to give you all some more practice with Lewis acids and bases for that. How are we doing on questions from the chat?
All right, looks like we have a few more questions.
All right, hold on. My OneNote. No, my OneNote's messing up again. I did restart my computer before I got onto everything in hopes that my Mac would love me. But my Mac does love me. It's the OneNote that doesn't love me. Okay, I'm ready.
All right, so two new ones. First one is, will we need to know solubility rules for this exam?
Okay.
And the next one is, will we need to calculate the pH of a mixture of a strong acid and a weak acid?
Of strong acid and weak acid?
Yep.
Okay.
And that's all for now.
Okay, cool. Okay. Did that one. So solubility rules. This is here's the thing about the solubility rules. For the most part, I can typically say no, you don't need to memorize your solubility rules. That being said, one of the things that does usually help when we talk about solubility, so here is an example of a solubility question off of my notes. Whoop, don't do that. Where it's asking for the molar solubility of lead 2 iodide, and there's a KSP in parentheses. You don't need your solubility rules for this problem because it basically gave you a KSP value, and therefore, since you have a KSP value, you're going to know that lead 2 iodide is relatively insoluble, which is why it has a KSP value. So a lot of times, very similarly to when we're doing acid and base problems, and we have to give you a Ka or a Kb for that weak acid or weak base, and therefore you could usually figure out that the other thing is strong. If you have a Ka or Kb for the weak thing, then the other thing is probably strong. But it was kind of helpful to be like, oh, that thing is strong. I know what to do with the strong thing. In that way, it's not bad to kind of have a general notion of some things that are always soluble. So that way, when you're looking at a list, you're like, oh, this is strong. I'm not going to have a KSP value for this, and I'm not going to look for a KSP value for this. So the only ones that I think are valuable for your old solubility rules are the ones that don't have any exceptions, because these are the ones that we use. So we typically use things with an alkali metal. Back to your periodic table, right? Alkali metals. Boom. Alkali metals, this group 1A. Always soluble. Lithium, sodium, potassium, rubidium. Yeah, technically cesium, francium, but those are rarer, so we're least likely to use those. The compounds containing the nitrate ion, you're going to see us use the nitrate anion a lot because it's always soluble. Acetate ion, chlorate ion. So to me, I don't think it's worth going through these things with all the exceptions. No, because anytime that there's a hydroxide and it's insoluble, we're going to give you that because it's math now. Phosphate, there's no reason to memorize these because we're going to give you a KSP value. But the things that are always soluble, a lot of times it can be helpful when you read the question to know that, oh, it's got a sodium ion, sodium's always soluble. It's got a nitrate anion, nitrate's always soluble. So those kinds of things can just be helpful to keep in mind, things you can ignore in solubility problems, things you don't need to worry about. So that's my personal opinion. Again, for a lot of the problems for solubility, we're going to give you a compound and a KSP value, and you don't need solubility rules for that because as long as you've got a KSP value attached to it, it's going to be okay. One of the things that you might take a look at, because I did grab these, is the old 2019 exams. On the very back page, they actually had tables. So that's actually how that one worked that year, was big old tables of KSP values. I didn't write the KSP questions this time, so I don't know how they're doing, if the KSP values are in a big table on the back page or if they're in the problem. I don't know yet. Ask me tomorrow. So that's what they did that year. And it just depends on the year as to what we do. Okay. So, hey, that was a quick question. Can't actually answer some things quickly for her. There. Solubility rules done. Calculate the pH of a strong acid and a weak acid. So this one. So we didn't do this one in the set of titrations, but what can happen is if we are, use some space. So if we had done something where we were titrating, let's go with 100 milliliters of 0.1 molar ammonia, and then we add 200 milliliters of a 0.1 molar, I want a different acid, HNO3, nitric acid. So for this, I didn't put in all the words, but this is another titration problem. So what we have here is we have the ammonia hanging out here. We have 100 milliliters of a 0.1 molar solution. So we have 0.01 moles of that. And then the other thing that you're adding into this is you're adding 200 milliliters. So we're basically adding 0.02 moles of HNO2 or HNO3. HNO3 is right there. So what we're going to wind up with as we do this one the weak species, so I've got to care about the conjugate species. 0.02, 0.01, and none. So as we start off with this, what I wind up with, 0.02, none of that, 0.01. Sorry. There we go. So I have equal moles of a strong acid and a weak acid. Now, let me go ahead and grab the Ka value. Actually, the Kb value. Kb value for NH3 is 1.8 times 10 to the negative 5. So therefore, I can know that my Ka value is 1e negative 14 divided by 1.8. 5.56 times 10 to the negative 10. Now, here's the thing. If it makes you feel better, you can calculate how many protons this ammonium ion is adding, because it is going to add some. It will. But look at that Ka value. It's tiny. It's really small. Also, think through all of the weak acid concentrations that you've done up until this point. Those amounts of protons in solution are very small. The strong acid is going to overwhelm the weak acid completely. And the pH is going to be determined only from the strong acid. You won't even know that the weak acid is there. You won't. So the way that we solve this problem is we just deal with the strong acid. So the strong acid, I've got 0.01 moles divided by 0.3 liters. That's my 200 plus my 100. So I'm adding those together. So as I add those together, I get 0.3. So 0.01 divided by 0.3 gets me 0.033, and my pH is equal to negative log of 0.033. I get a pH value. Just gonna finish this problem and then I'll make teams go away again. So my pH is equal to 1.48. We can calculate the effects of that ammonium ion, but it's going to be so incredibly tiny. It's going to be something like 1 times 10 to the negative 6, 1 times 10 to the negative 5. It's going to be so many decimal places out that it rounds away. You won't actually see it in the calculation. So when we think about doing a pH calculation with a strong acid and a weak acid, we ignore the weak acid. It's so ineffective at being an acid. The strong acid overwhelms it, and we just deal with the weak acid. We just deal with the strong acid because of that. So you can do a calculation that has both. And when you do that, you just deal with the strong acid. Trick work this time. So you just deal with the strong acid. So you can do that. When you do that, it's just a strong one. So just a strong species matters at that point. Hey, I got another titration problem in. What do I have left? Salts and pH. Let's do salts and pH. So there are two. So this is actually another time where I'm going to recommend the end of chapter problems for these. So when you talk about salts, there are two main kinds of problems. So one kind of problem says something like, what is the pH of NaNO2? I need a concentration, 0.5. Of a 0.5 molar NaNO2 solution. And it's going to say Ka of HNO2 equals, where is it? Over here. Yes, you bail me out. 4.5 times 10 to the negative 4. 4.5 times 10 to the negative 4. So if it's asking you to do a calculation, this is going to feel hopefully a little similar to some of the things we've done earlier in this exam review. I have sodium nitrite. That means that I really have a sodium ion and I have a nitrite ion. when it's asking me to do a calculation, this usually helps me out a bit because I need a Ka value or a Kb value to do this. So this becomes a game of recognition. One of the things you do have to recognize is the fact that this sodium is not going to contribute to the pH. I know that in two different ways. One, that sodium ion that I just put the great big X through is an alkali metal. It's in group 1A. I know that I've scribbled all over this. Let me erase some of this. So that sodium ion is right there. Oh, I like pink because it can draw on it better. It's an alkali metal. It's group 1A. Things that are hanging out in group 1A and most of what's hanging out in group 2A, but not beryllium, are neutral. So all of these guys are neutral. They're not acidic, they're not basic, they're neutral. They are neutral metals as far as what happens when you throw them into water. The rest of your metals, your cations, will be slightly acidic and will contribute to the pH. But sodium, potassium, rubidium, calcium, strontium, neutral, all neutral. The other way, you might know that, is when we think about what could happen here, we need to think about the fact that if my sodium could do something, what it would do is it would grab a hydroxide. If it could do something, but we know this doesn't happen. We know it doesn't happen because that thing is a strong base. As a strong base, we know that this always dissociates 100%. So we don't ever form sodium hydroxide in water. This happens 0% of the time. That doesn't happen. We know that because 100% of the time, our sodium hydroxide dissociates. So we know that this one happens 100% of the time. So my sodium hydroxide dissociating, that's a strong base, happens all the time, means we never form sodium hydroxide in solution. It's always a sodium ion and a hydroxide ion. Even though sometimes we draw it all together, in water, they're always separate. So that sodium ion cannot do anything. That leaves me my nitrite ion. So my nitrite ion, I know two things. One, I know that my nitrite ion is not the nitrate ion. So this guy is a strong acid, which means this one is not a strong acid. And I know that that may seem a little bit strange to be like, so it looks kind of like a strong acid, but it's not one, so therefore you know that it's weak. But this is a recognition kind of a game, and we have asked you to memorize your strong acids. So a lot of times we actually do give you things that look like strong acids but are not, in the hopes that that helps you with recognition instead of giving you something you just completely never seen before. So we do tend to use things like this to help with recognition. That really is why we do that. The other thing is that if it's in the problem, hey, here's this beautiful Ka value. So this is a kind of a nice hint that the thing that they gave you is related to something else. From here, what we need to do then is we want the pH. We know that what we have is the nitrite anion, and we have a Ka value for the hydrogen for what is this called? For nitrous acid. There we go. Like, I know my nomenclature. So we have the Ka value for nitrous acid. We have the nitrite anion. Since we have the nitrite anion, what we should be able to think through is, since this is a negative charge, It's a base. It's not the acid. So this is going to react with water to form that. And hydroxide, because it's a base. So there is a lot of recognition that goes into this, but your anions have the ability to become bases. Your cations might have the ability to become acids. That's how this one works. It's a water, so I don't care about it. The problem tells me I have 0.5 molar. None of this, none of this. We're back to ice tables because I just have one thing in solution. I would like to know if I can use the X is small approximation. What I have here is I have hydroxide. Since I have hydroxide, that means I have to have Kb. So Kb by definition has hydroxide in it. So I need a Kb value. They gave me a Ka value. So I have to do some math. 1 times 10 to the negative 14 divided by my Ka value, 4.5 times 10 to the negative 4. So my Kb value is 2.22 times 10 to the negative 11. We'll still go ahead before I move on to use my X is small approximation. We'll still double check it. That's a pretty small number though, so I'm feeling really good about this one. So I'm still going to do 400 times my Kb value. So 400 times 2.22 times 10 to the negative 11. It's in fact very small. 8.89 times 10 to the negative 9. That is in fact smaller than 0.5. So we can use X is small. Since we can use the X is small approximation, and y'all have seen ice tables a bit by now, I'm actually going to skip a couple steps. So one of the things that you can use, if it is helpful to you, is once you know you can use X is small, and we're using a Kb value, we can actually basically speed this up to say that my X, which is going to be my hydroxide, because I'm using Kb, is equal to the square root of my Kb value times my original concentration. If you do the ice table algebra, this is what you wind up with. So this winds up being a little bit of a shortcut, just because y'all have gotten very familiar with ice tables in weak acids and weak bases. So sometimes you can shortcut a little bit. This will not work with solubility, by the way, because KSP is more complicated, but you can do this for Ka and Kb values. Times 0.5, and then I just square root everything. 3.33 times 10 to the negative 6. Molar, that's my hydroxide concentration. What did the problem ask me for? Am I done? No, not done. Of course not. pH. pH. Of course I did. Why didn't I cut myself some slack? So what I'm going to go ahead and do is solve for the POH, which is the negative log of hydroxide. I don't know why I was so hopeful that I was not going to have to solve for pH again, because that's all we're doing is solving for pH so that we can make sure we can demonstrate how to go back and forth a whole bunch. Every once in a while when people ask me, like, what are some things that I do in my personal life, I'm like, I need you to understand that I trick myself really easily. For most people would not think that these things would work on an intelligent human being, or even just a human being that's awake, but I tricked myself a lot. So I got a basic pH. My pH is greater than 7. Does that make sense? Let me go back. Hey, I have a salt. My salt involved a base, not an acid, and no acid. So I had a basic salt. My pH should be greater than 7. My pH is greater than 7. Awesome. Yes, I like it. Good. With salts, this is one potential kind of question that we can ask, which is solve for the pH of a salt given some information. So that's one option. The other option is to ask you which of the following is an acidic salt or which of the following is a basic salt. In that case, what you're looking at is a lot of recognition and a lot of identification. So, for example, we could have something like sodium chloride and ammonium chloride, and we actually are just going to use the thing we did before, NO3, NO2. For each one of these, what we need to think through is really each one of these is 2 separate ions, and I therefore need to address each individual ion. Now, we've already spent some time talking about alkali metals. So I've got sodium and potassium. Sodium and potassium, they're both alkali metals. So I know that my sodium and potassium are going to be neutral. I don't care about them. They're neutral. They won't contribute to the pH. Then I've got chloride ions. These might remind me of HCl, but remembering again that hydrochloric acid is another strong acid, which means it goes 100% in the forward direction, which means that chloride ion is never going backwards. So chloride is also going to be neutral because that chloride ion does not have an ability to pick up a proton out of the water and make hydrochloric acid. It's never going to happen. So those chloride ions are going to be independent, neutral, hang out alone. So I got rid of all the neutral things, we think. Now I'm to recognition gains. So this one is where that, granted, we just did a problem on it. So this NO2, basically you're like, all right, well, it's negative. So what does it look like if I slap a proton on there? Since it's already negative, what does it look like if I added the proton to make it neutral? And then this should hopefully look like a weak acid. Because again, it's not the strong acid of HNO3, it's the weak version that looks similar. So since that's the weak acid, my NO2 minus should be classified then as a weak base because it's the conjugate species. It's missing the proton, it's the conjugate species. This is a weak base, so we refer to this one as a basic salt. This top one, since we got rid of everything in it, is a neutral salt. This one, I've got NH4 plus. Since it's got a positive sign on it, I'm going to go ahead and look at what it looks like if I took a proton away. And now I see something that looks familiar again. So I've got that NH3 that we usually use as a weak base in a lot of our examples. So what I have in solution is the NH4. And this should remind me that this is a weak acid because it's the conjugate acid of our ammonia. So this then is an acidic salt. One of the things that helps with identifying salts when there's no necessarily Ka values or Kb values to help you out are those practice problems at the end of the chapter, or are those Alex assignments that y'all do, because a lot of that then is in practice. The practicing and the looking at different chemical species and becoming a little bit familiar with what some common acids are and some common bases are, then help identifying with acidic and basic salts. But you'll notice that in order to do all of this, I did break everything down into the ions and then analyze everything. So I know some people will just be like, I guess I should just be able to look at it when it's all together. And personally, I prefer to separate everything out because it looks more familiar to me. So to me, NH4 plus and seeing that plus sign is more helpful to thinking about that as the conjugate acid of ammonia than seeing it all grouped together in the salt form when I just see NH4Cl. So separating those out usually is helpful to me when I'm looking for identification. Take a look at the question list. Okay. Salts and pH. Conjugate acid base pairs. So if the person that asked about conjugate acid base pairs, if you don't think I did enough of that, let me know. Because at this point between titrations and salt questions, I think I've addressed that. Again, if not to your satisfaction, then give me a longer question so that I can better look at that. A pH based on the strong present species. I think we've been doing that through the titration problems because I think that was a lot of identifying what you have left in solution and therefore deciding what to do. So I think we have done that. I'm left with, I have not done a strong titration, I'm aware. And so I'm going to put that in parentheses. I've not done a strong titration. Almost a full box. I've not actually done a buffer problem. And we have not talked about indicators. Okay. I also have like 15 minutes left. Let's go and take questions from the chat and see where I'm doing, how I'm doing on questions so far.
All right, we just have 2 more questions.
Okay.
So the first one is, can we use the way Alex shows us to solve titration questions?
Okay.
And the next one is, could you go over the common ion effect and problems based off of it?
Okay. So I have to admit, I have no idea what the Alex version of titrations is. But I'm going to go with yes, because one of the things that I've learned about Alex is Alex loves math. I don't know if you've noticed that in their explanations. Alex loves mathematics. It assumes you love algebra a lot. So yes, whatever way Alex is doing titrations, that will work. I know all the instructors kind of have their personal preferences. My personal preference is to react everything in moles and go from there. I think Alex uses millimoles. So before we started doing titration problems back at like 4:10 p.m., I think I said something about the fact that if you prefer millimoles, then you are welcome to use them. And that was for people that like Alex. If that means something different, then I don't know what it means. But to the best of my knowledge, Alex does use millimoles. And those work. Those work great. Those work fine. If there's something else that you mean by that question, I'm still going to say yes, because again, Alex does a lot of stuff with mathematics and algebra. And there's always different ways to solve the same problem. Works just fine. Common. So I'm actually going to. So the thing is that with common ion effect, so this is actually way more common in solubility problems than it is in acid-base problems. In acid-base problems, we actually just flip over into buffers. So I understand that common ion is like section 18.1, but that all it's actually trying to do when it's in the very beginning of the chapter is transition you from thinking about acids and bases as separate entities and thinking about them going into the same thing together to think about buffers. So if you're thinking about common ion effect, with pH, that's a buffer problem. And we're not going to do one otherwise. But if we're trying to think about this as a solubility problem, then we can do something. So let's actually grab the one that's been hanging out, not the second law of thermodynamics. I wanted something that has a KSP value to make my life easier. Is it this one? No. This one. This will prove great. So, because we haven't done any KSP. And I'm supposed to do indicators and buffers over there. I kind of expect there to be another titration problem thrown into the chat at the last minute. But since we haven't done any KSP problems, let's do a KSP problem. So I'm going to do this one as is, and then I'm going to do a common ion effect problem. So I am aware that this is not a common ion effect problem. But first, for those of you who have not been introduced to KSP, welcome to KSP. So just to refresh, KSP is where we're basically going to assume that whatever the heck this thing is, it's a solid in equilibrium with some teeny tiny amount that dissolves. Now, as we do these, aqueous, as we do these, one thing that you will need to pay attention to is that stoichiometry, because you're going to have to build that yourself. So that is part of the problem. As far as solving for molar solubility, when we solve for molar solubility, what we're really solving for is X. Now, your textbook will use a different variable for this. That's really just to emphasize the fact that this is a solid, we don't care about that, plus X plus 2X, X, 2X. It's going to emphasize the fact that what we're looking for is we're looking for something that's actually in a 1-to-1 ratio with this. So even though this is a solid, this lead to iodide is a solid, and therefore it's not involved in our equilibrium expression. When we're asking for molar solubility, we're trying to ask how many units of lead to iodide dissolve. So that's what we're trying to ask. We're trying to ask how many units of lead to iodide dissolve. So I need something that's in a 1-to-1 ratio with lead to iodide, and that's X. For every 1 lead to iodide, I have 1 lead, and that's going to be my X. Even if there was stoichiometry all over the place, as long as we're just using those coefficients, 1X will be your lead to iodide. I know Alex sometimes used other fractions and things, but that X should just be equivalent to 1 unit of lead to iodide. So I'm going to solve for my molar solubility, which is X. KSP is 1.4 times to the negative 8. KSP is equal to lead times iodide. My iodide concentration squared. Hey, we haven't done that in a long time. So a reminder that in equilibria, your coefficients become exponents. It's been a long time since we did that. I know some of you are very confused. This was a chapter 16 thing when we did equilibrium. I know it's weird. You haven't seen it in a while because acids and bases are all 1-to-1 ratios. That's the other reason why I wanted to do this, is so you could take a look at it. So then I'm just going to plug in. So I wrote my K expression from my equation, which yes, I did have to write myself. And now I'm just going to plug in with all those X's. So my KSP value is 1.4 times 10 to the negative 8. 0.4 times 10 to the negative 8. Did pull that correctly, good. And then my lead is X. And my iodide is 2X, which is all squared. Therefore, 1.4 times 10 to the negative 8 is equal to X times this squared term is distributed over both of these. That is 4X squared. 1.4 times 10 to the negative 8 is equal to 4X cubed. Then I can divide both sides by 4. I get 3.5 times 10 to the negative 9 is equal to x cubed. Then I have to get out of this cubed thing. There's 2 ways to do this on your calculator. My personal favorite, because I never want to, I don't usually remember what order I have to put in all the numbers. So you can use fractional exponents. So I'm just going to raise everything to the 1/3 power. So in your calculator, no joke, this looks like 3.5 e negative 9, and then the caret, and then in parentheses, 1 divided by 3. If you can do cube, there is a way to do cube roots, but this is just easier for me personally. If you want to do it the other way, practice. That's what you're practicing for. So practice with your calculator so that you can be able to get in and out of cube roots, because you might need that. Or you might need larger, weirder things. So this is my value of x. This is both the amount of lead that's in solution. This is also the amount of my lead 2 iodide that dissolves. So this is the molar solubility of lead 2 iodide in water. Now that we've done some math, and I've shown you guys my personal favorite of fractional exponents, honestly, that's because of how these calculators work. Some people are really good with these calculators. I'm pretty good with these calculators until I have to do not a square root. And once I have to do not a square root, I need a new tool, and that's why I use fractional exponents. You don't have to. There's a different way to do it. Practice. So what we're going to do is we just calculated this in water. We're going to do it again, not in water. We're going to add a common ion. What is a common ion, you might ask? Well, I have lead and iodide in water. So instead, I'm going to do this in a easy numbers, y'all, easy numbers. In a 0.1 molar solution of sodium iodide. This is a common ion effect problem. So because of the KSP value, I'm going to focus on lead. Also, I'm still going to solve for the molar solubility of lead 2 iodide. But now, something's changed. I don't have water anymore. So while this is still a solid, and I still don't have any lead, I have iodide in solution before anything begins. So in the initial, I have sodium iodide. So we got to think about this for a moment. Sodium iodide, when that dissociates, I should get a sodium ion and an iodide ion. Remember how I mentioned that thinking about solubility rules, that it wouldn't hurt to know that that sodium ion is always soluble and therefore we don't care about it? This is when that's useful. So I'm not thinking about that sodium ion. I just want to know how many iodides I've got. 1. I got 1. So this molarity, I'm just going to use it as is, because this is the constant. This is my column for where my iodine goes. I have 0.1 molar of iodine, so it goes in there. I still have no lead, so this is going to be plus x. This is going to be plus 2x. That's also going to happen. I got x. I got 0.1 plus 2x. I'm still solving for molar solubility with a KSP value. We are still going to use an x as small approximation because my KSP is still lead times iodide squared. But now as I'm solving for molar solubility, I've got 1.4 times 10 to the negative 8 is equal to my x times 0.1 squared. because that plus 2x, we're using the x is small approximation. I'll go ahead and write that out. So people are not like, you forgot it. I didn't forget it. I got rid of it. X is small. So we solve. 1.4 times 10 to the negative 8 is equal to x times 0.1 squared. 0.1 squared. 1.4 times 10 to the negative 8 is equal to x times that. 0.4 times 10 to the negative 8 divided by 0.01 gets me 1.4 times 10 to the negative 6 is equal to x. So the amount of lead to iodide that can dissolve now is 1.4 times 10 to the negative 6 molar. What should have happened? This number should be smaller than my other number, because a common ion effect, what it should do is demonstrate equilibria. There was a time where we would do equilibria problems and we would talk about things like which way is the reaction going to shift if I add this or I add that. What's going to happen and which way is it going to shift on me? Well, think about it. If I'm starting off with all of this iodine, my equilibria should shift back towards the solid. So I should actually have less of the solid to be able to be dissolved than when it was all just water. So I have 1.4 times to the negative 6 with the iodine. Without the iodine, I had 1.52 times to the negative 3. So more of this could dissolve when it was just in water than when we added a common ion. So that's a common ion effect problem where you're adding something that's already there. So common ion means you're adding something or something's in solution that already had to do with the thing we were worrying about or the thing we were working with or the thing we were thinking about. So for lead 2 iodide, I had two choices. I either had iodine or I had lead. Those were the only two species I was going to worry about because of the KSP value that we started with and that lead 2 iodide. So that's a common ion effect problem. One other thing to note, I did keep going ahead and writing out these KSP values with the lead and the iodine in them. I'm doing this because I'm trying to remind y'all what equilibria values look like. This is something that sometimes people will get a little bit excited about where all the coefficient goes. And so it's part of the definition that while, yes, because of the stoichiometry, there is that 2x for the iodine. And when we actually needed to put in x, we used that. But when we were just doing KSP expressions, there's only exponents. There's no coefficients in a K expression. That was true back when we had chapter 16 and we were doing equilibria constants just for fun and doing whatever we could think of. And we had KC expressions and KP expressions. It's actually been true the whole time we were doing KA and KB expressions. Just everything was 1-to-1. Now that we have stoichiometry again, just like we had when we did chapter 16, we still only have coefficients. Still only have exponents in the K expressions. Still only have exponents in the K expressions. When you get into the X's, then we have coefficients. But when you have K expressions, just exponents. I know there's more KSP stuff we didn't talk about. I didn't actually do a buffer problem. So in the follow-up video, I will do at least one buffer problem. I did skip over the strong titration. So I know I have to do a strong titration. Oh, choosing the best indicator. I didn't do that. That's why I wrote things down. We did the common ion effect problem. Did that. Other questions out of the chat. It is 6 o'clock, so these will, unless they're super short, they're all going to be for the follow-up video. But what other questions do we have?
We got 2 more questions. One more was, can you explain buffer capacity? And they said they want to understand that more.
Okay.
All right. The next one is, for the molar solubility with the common ion example, should the initial concentration of I be 2 times 0.1 equals 0.2 because of the coefficient?
Excellent. I'm going to answer that question.
Okay.
That question I'm going to answer. Because the answer is no. So here is the deal. This initial concentration. So I got excited though. I don't know if you noticed. I got excited that somebody asked me that question. I got excited because that's a really common question. And honestly, it's something that I should have mentioned. That's why I got excited. So that initial value came from the solution of sodium iodide. So that's where it came from. So since my initial value came from a solution of sodium iodide, for every 1 mole of sodium iodide, I only get 1 iodide ion. So I could go ahead and say 0.1 molar of sodium iodide, I only get, for every 1 sodium iodide, I get 1 iodide. So everything stayed in a 1-to-1 ratio because of the solution they gave me. That's actually where that matching came from. So that's how I knew that, and that's why it's just the 0.1, is because it was given to me in the beginning. That is always a good thing to think through, is where are my numbers coming from? How do I know that? Where did I get that from? Because if this had been a different solution, it could have been different. So just to make things a little weird, if this had been aluminum iodide, and we're just going to assume this is completely soluble, it might not be. But this would have given me a different stoichiometry entirely. This would have given me 3 iodines. And then if this is my 0.1 molar aluminum iodide, then for every 1 aluminum iodide, I would have had 3 iodides, and my iodide concentration would have been 0.3 molar to start off with. So that initial concentration of iodide is coming from the sodium iodide concentration. It's coming from whatever the problem gave us. It's not coming from the lead. So you do have to kind of figure out where is it coming from, and therefore what is the concentration. So because that initial concentration is coming from the sodium iodide, it's just in a 1-to-1 ratio. But that's a really good question, and it's something that I should have emphasized better. So I'm really glad that you brought it up. So I've got my assignments for the follow-up video. If there's more stuff in the chat, then I look forward to that email. It's after 6 o'clock.
All right, wonderful. Well, thank you everyone for attending. Again, the recording and follow-up video will be posted in the coming days. Yeah, good luck on your exam next week.